This video is about the first derivative test, finding intervals of increase and decrease. Derivatives tell us quite a lot about the behavior of different functions. And the first thing that we're going to look at is finding intervals of increase and decrease. So suppose we have a function f defined on some interval. Remember that we say that a function is increasing if you have some x sub 1 less than x sub 2 and the function value at x sub 1 is smaller than the function value at x sub 2. That means that we're increasing. And similarly, if you have x sub 1 to the left of x sub 2, and the function value at x sub 1 is bigger than x sub 2 on an interval, then the function is decreasing. Now you'll notice that the two lines that I just drew, the first one's not perfect, but the second one is kind of like a tangent line. And it looks as though the tangent line has a negative slope. And in the first one, let's see if we can't fix that just a little. In the first one, it looks like the tangent line might have a positive slope in that interval. So really, that is the first derivative test. It says, suppose you have a continuous function on an interval I that's differentiable at all interior points, and the derivative is positive at all interior points, then it's increasing. And if it's negative on all interior points, then it's going to be decreasing on that interval. So let's take a look at an example. Let's graph this particular function using the information about critical points and finding intervals of increase and decrease. So the first thing I'm going to do is say, well, this is a polynomial. I know that it's continuous and I know that it's differentiable everywhere. I'm going to find the derivative. The derivative of this function is going to give me x squared plus x minus 6, just using the power rule. And I can see very easily that this factors as x plus 3 and x minus 2. So my critical points, CP, are going to be at negative 3 and also at positive 2. So I'm going to make what we call a line chart. This is for the first derivative. And I'm sure that you've noticed at this point that we're going to be using the function and the derivative, so annotating things correctly is super important. So here we are at 0. We have a critical point at negative 3, and we have another critical point at 2. Please put a dot on these. Don't just leave them open. And I just want to test my intervals from minus infinity up to minus 3, bracket, minus 3 to 2, and 2. Let me back up just a little bit. I don't want to use these brackets, and I'll tell you why. When we say it's increasing and decreasing, it's increasing on the interior points and decreasing on interior points, so we don't want to include them. All right, so I'm going to test in this interval negative 4, and I want to know what is the derivative at negative 4, and I get 6, which is a positive number, and that means that in that interval, the function is going to increase. Similarly, I'm going to test 0. I can choose anything in the interval, but choosing values that are easy to calculate is always nice. So this is negative, which means that in that interval it's going to decrease. And then I'm going to choose in this interval from 2 to infinity, I think I'll just choose 3. I also get a positive value. That means in this instance it increases. Now if we use our first derivative test, we'll notice that here it increases and it changes to decrease And over to the right, it decreases and then it increases again. And that becomes important for us. So let's find some points just to help us graph this. The y-intercept in this case, if we let x equal 0, is 4. And let's find the function value at -3 and the function value at 2. So it turns out the function value at -3 is 17.5, and at -2 it's 10/3. So we're ready to sketch. So you'll notice that I have created a scale that will allow me to graph this 17.5, and that the scale on the x-axis is different than the scale on the y-axis, just so I can fit everything on. So let's graph these 3 points that we know first. 0, 4, -3, 17.5, and 2, -10/3. And we know that this graph is going to increase to -3. It's going to decrease to 2, and then it's going to increase again. And so filling that in with a nice smooth curve, we get the function f of x. It does not have all of the properties of f of x. It has maximum, minimum, and the y-intercept. But we don't know where it crosses the x-axis because we didn't take the time to find that. But it is just a sketch, and we've done a really great job. Now, what I want you to notice, and this is going to lead to our first derivative test, is that when a function increases and then decreases, as it does at -3, we have a maximum point. And when it decreases and then increases, we have a minimum point. And that is essentially the first derivative test. So the first derivative test tells us -10 that if a derivative changes sign from positive to negative, so increase, decrease, then we have a local maximum. If it changes sign from decrease to increase, we'll have a minimum. This one's max. If it doesn't change sign, so it's positive on both sides near C or negative on both sides, then it does have no local extrema. That can happen very often with, let's give an example here of x cubed. When a function flattens out at a point, so in this particular case it flattens out at 0, but it is increasing and increasing. So there's no max or min. We do have a critical point at C, but it doesn't happen to be a maximum or a minimum. The next theorem that we have says if we only have one maximum or minimum, then it has to be an absolute maximum or minimum. Okay, so let's take a look at an example. We've got find the local extrema for the following function, x times e to the minus x. So first we're going to take the derivative of this function, and we're going to get f prime of x is first times the derivative of the second plus the second times the derivative of the first. I'm going to factor out an e to the minus x, so this is still my derivative, and it's going to leave me with minus x plus 1, or alternately, I'm going to rewrite it because I don't like it that way, 1 minus x. So to find my critical points, I want to know where is this undefined, and it's never undefined, and where is this 0. So when does e to the negative x equal 0? That answer is never. Remember, that's the graph of e to the negative x. We have that asymptote. And when is 1 minus x equal to 0? And we get x equals 1. So we only have one critical point. So that means that it's either an absolute max or an absolute min. So we are going to plot on our number line 1, and then we're going to test something to the left and something to the right. So let's find the first derivative at 0 and the first derivative at 2. So the first derivative at 0 is going to give you e to the 0, which is 1, and 1 minus 1 is, or 1 minus 0, so this is 1. This is positive, so to the left here, we're going to be increasing. At 2, f prime of 2 is e to the negative 2, or 1 over e squared. And then there's a negative, because if I plug in 1 minus 2, it's negative 1. So this is approximately negative 0.135. So this is negative, and because it increases and then decreases, we have a local max at x equals 1. So let's find out what the function value is at 1. That will be 1 times e to the negative 1, or approximately 0.368. So remember, your maximums and minimums are your y values. So we have a local max of 0.368 at 1. Okay, let's take a look at the next example here. Let's verify that x to the x has an absolute extrema on its domain. So it would be nice to know what is its domain. Well, 0 to the 0 is an indeterminate form. So that means it's undefined at x equals 0. So our domain is going to be negative infinity to 0, union 0 to infinity. We would now like to find the derivative of f of x. Well, f of x, x to the x, leads us to believe that we're going to have to use logarithmic differentiation. So I'm actually going to take the natural log of each side, and then I'll get the natural log of f of x equals x times the natural log of x. So I'm using natural logs to allow me to bring this exponent down onto a level that I can deal with. So now when I take the derivative, the natural log of f of x is 1 over f of x times f prime of x. On the right-hand side, we get a product, the first times the derivative of the second, plus the second times the derivative of the first. And so we get f prime of x over f of x is 1 plus the natural log of x. Now, what I need to do at this point is I'm only looking for f prime of x, so I am going to multiply both sides of this equation by the function, and I will finally get that the derivative is 1 plus the natural log of x times x to the x. What is the domain of this? Well, since a natural log, we cannot take the natural log of anything that's 0 or negative. Our domain here is going to be x greater than 0, or alternately 0 to infinity. So let's now find our critical points. Critical points are where the derivative is 0 or when the derivative is undefined. Well, we know that it's undefined if x is less than or equal to 0. And that's going to help us in a different way, because when we make our chart, what we know is nothing back here makes any sense. So we're just not going to deal with anything back there. And then we have to ask ourselves, when will 1 plus the natural log of x equal 0? Well, that gives us the natural log of x equaling -1. So e to the -1 equals x, or alternately 1 over e. So 1 over e is approximately 0.368. So if we now test some values, we might want to test, for example, 0.1 or 1. So this is my derivative graph. So I want to find the derivative at 0.1 and the derivative at 1. And I'll let you do that in your calculator, but you should get the derivative at 1 is 1, and the derivative at 0.1 is -1.03. So we have negative derivatives and then positive derivatives. So it'll be decreasing and then increasing. So using the first derivative test, we have a minimum at x equals 0.368. So let's find the function value at 0.368. So that would be, let's see, 0.368 raised to the 0.368. And of course there's some rounding here. We get 0.6922 approximately. So the minimum is 0.6922, and that occurs at 0.368. So keep in mind the minimum is the y value. That concludes this video on first derivative test. Hope you have enjoyed it, and I'll see you next time.